You are. All right, let's do this. Thank you for letting me in.
Yeah, you're welcome. Okay, so we're starting here. This is lecture 11. It is Friday of reading week. And as promised, I am talking about protecting groups. So the main goal here is that I'm going to put together a lecture. There's going to be slides, there's going to be voice and all that, and video. I'll turn on my camera so there's video. So there'll be the works. And then we're going to go through some examples in class on Tuesday as a group to work through some of these things, because this is kind of where we can sort of make use of this to actually access different sugars. And I'm trying to minimize my Zoom window. There, I have succeeded. Okay, there we go. So, a few lectures ago, it was lecture 7. I gave a list in lecture 7 of a series of protecting groups that we will be looking at. And the first one we're going to start with is the acetate protecting group. So, the acetate protecting group is acid stable. So what we're going to do is for all of them, I'm going to give 3 main conditions that they're stable to. Are they stable to acid? Are they stable to base? And are they stable to hydrogen gas? Because those are our 3 main protection, deprotection strategies. Now we're going to see some other ones, but those are the ones that do dominate the field. And so it's relevant whether we're stable to that. So we're acid stable. We are base unstable. Very unstable for different reasons. We're going to mostly worry about nucleophilic base. And hydrogen stable. So again, the acetate protecting group is that. It isn't, well, something special. It's an acetate. And so we are going to attach that to our oxygens of our sugar. Now the way we do that is we can take our sugar, and I think at the end of last class we were discussing the fact that we can take a sugar alpha beta mixture, and we had 2 sets of conditions. We could either treat that with acetic anhydride and pyridine, and we get the peracetate, mostly alpha. Peracetate means it's acetylated everywhere. That's what the per means. Like I'm going like as if I have another per on the tip of my tongue, and I don't. Or we could have taken sodium acetate and acetic anhydride. Notice I moved acetic anhydride into the bottom there because it is actually the solvent. It's also a reagent, and we get mostly the beta. And I think we discussed this in a bit of detail last class over why that might be the case. But let's just quickly mechanistically cover what's going on here. You have an alcohol, and you treat that with acetic anhydride and pyridine. Pyridine is not a strong enough base to deprotonate an alcohol, so I hopefully will not see that. What we're doing instead is we're getting nucleophilic attack of the alcohol onto the anhydride, cleavage of the anhydride, release of acetate as a side product, and then acetate or pyridine, either will work, is going to just scoop up that extra proton, which gives us the acetate. Now, the pyridine, of course, is going to end up with it because acetic acid is going to react with pyridine to grab the proton and generate acetate. So what we're doing here is we're basically using acetic anhydride to do this. Now, you don't get any selectivity with acetates. You can't. Acetates kind of blanket it. You can't really figure out, oh, I only want to protect this sugar or this alcohol with the acetate on the sugar. You kind of do all the alcohols you've got. Um, Theoretically, you can get slight selectivity for the C6 position, but I say that theoretically. I would never, ever try and do that. We are going to show some which will give you that selectivity, but acetate's not one of them. Now, I'll take the acetates off. Let's see, you're starting with a slightly different molecule. We've got a thioether up there. We've got acetates everywhere. We're going to treat that with sodium methoxide in methanol. And so what happens here, and the way you make this is you take some methanol, you drop in a little chunk of sodium, and it smokes and fumes and zips around everywhere and slowly dissolves and makes sodium methoxide and methanol, generating hydrogen gas. And so what's happening here is we are getting basically a nucleophilic ester hydrolysis. So you have an ester, you have sodium methoxide, it attacks the carbonyl and releases the alkoxide, which is then protonated by methanol. Workup for these reactions is always some sort of acid. The most convenient one to use is actually this polymeric resin called Dawix resin. You just add a little bit to your reaction mixture, stir it around, and filter. And the Dawix resin absorbs the sodium and swaps. This is going to be a sodium counterion. And swaps the sodium for a proton. And then the sodium is bound to your Dawix resin, and the proton is bound to your alcohol. It's nice because everybody likes a workup that just involves filtering. So this is how you deprotect the acetate. There are other ways to do it. They're not particularly important. They're all kind of relying on this basis of nucleophilic attack. So, strong nucleophilic basis, nucleophilic. Nucleophilic? Okay, I'm getting into my head. Deprotect the acetate. So, no selectivity. Easy to use. Easy to take off. They give you that anchiomeric assistance at C2, which is kind of handy. And they also make alcohols less reactive. And they deactivate or disarm the sugar. So it's less likely to make an oxocarbenium. So that's relevant. If you want to make one that's more likely to make an oxocarbenium, you want an electron-rich ring. Acetates pull electron density out of the ring. So that both makes any alcohol that's free on a ring less nucleophilic because it has less electron density. And it makes it harder to make an oxocarbenium because in an oxocarbenium, you're making a plus charge on the ring. And you want to be able to donate electrons into that. And if you have acetates on your molecule, they're pulling electrons out, and that makes it harder to donate electrons because they're pulling. So acetates kind of make your molecule less reactive. The second main class of protecting group is the benzyl protecting group. So this is that. It's a CH2 attached to a phenyl. It is acid and base stable. and it is hydrogen sensitive. So you cleave it with hydrogen gas. So the way you put this on is generally you take, again, we lack selectivity with this guy. What this is basically the hydrogen sensitive version of the acetate. And normally it is something like sodium hydride, benzyl bromide, and DMF as solvent. Works best. You can do this in THF as solvent, generally 0 degrees. So you pre-add the sodium hydride. Sodium hydride is a very strong base. It deprotonates each of the hydrogens in turn, so you get a tetraalkoxide. So this molecule is sitting around there with 4 O minuses. You add benzyl bromide, it attacks the benzyl bromide because benzyl bromide is a really hot electrophile, and you end up with the benzyl protected sugar. So mechanistically, what's going on there? Sodium hydride. So notice that to make this, we have to use a strong base, which makes making this incompatible with having an acetate present. There are other ways to make this. I'm going to show that in a second. Just want to see if I've got a good one. No, it's a stupid example. I'm not going to use that. No, it's not that stupid. No, it's still too complicated. This doesn't work as well, but it'll still work. So what you can also do alternatively, because you can treat that with benzyl bromide, silver nitrate, and often a weak base like DIPEA. And so again, silver does what we've been seeing silver do all course, which is pull away a bromide. On a normal alkyl bromide, that's not sufficient, but when the bromide is attached at the benzylic position, that's already a weakened carbon-bromine bond because the nascent carbocation at that carbon is stabilized by resonance from the aryl ring. And so you do have added stability that does make silver enough to weaken that carbon-bromine bond enough that an alcohol can now act as a nucleophile. So this is a little bit more problematic. You do need to add heat, but you will get there in the end, and you don't use any strong base. And this is stable to acetates. So we've seen acid stable or base unstable, hydrogen unstable. Let's move on to acid unstable. And these are the silyl ethers. And so what we've got here are a series of them, and they all work basically the same. Again, let's say we have an OH, something at the anomeric position, and let's say we're using TMS chloride, and we generally use imidazole as a base for these. And I'm not really sure why. I'm going to say, I can always say it's a match of pKa values. I always find that relatively unconvincing. But it always gives you higher yields. It's just a cleaner reagent. And so we end up with TMS at every one of the spots. If you can't remember what TMS is irritating because it means trimethyl and also tetramethyl. But in this case, it's trimethyl. So this is base stable, hydrogen stable, acid unstable. I actually think TMS is so unstable that it's kind of useless as a protecting group because it just falls off as soon as you look at it wrong. TMS is not stable on columns or anything like this. So what we're often doing is we're going to switch to a slightly more stable version of this. So what we'll see more often is TES. This is one I really like. That is triethylsilyl. So I'm just going to put TMS up here. Delete the chloride. Just trying to take a look at what are the ones I'm talking about. Okay, so I'll put TBS on. TBS is sometimes called TBDMS. You will see both. TBDMS is more accurate. It's terbutyl dimethyl silyl, but people just call it TBS because TBDMS is too long. And so we have a terbutyl group there. Now we've added more steric hindrance. It's more acid stable than TES until we can get down to something like TIPS, which is triisopropyl silyl. This is in terms of increasing acid stability. So what does that mean? Well, what it means is that if you have OTMS and you hit that with acetic acid, the TMS falls off. Whereas if you have TES, you're going to need something more like HCl or TFA. You need a stronger acid. For the TBDMS, you're looking at some of the stronger acids generally. And for TIPS, if you want to take it off with acid, you're using concentrated HCl. Now, the problem, of course, with concentrated HCl is it's concentrated HCl, so it's probably going to damage the rest of your molecule. So it would be another good way to do this, and that's that all silyl-protecting groups are very sensitive to fluorine. So tetrabutyl ammonium fluoride. Will always do the trick, and that's just going to take it off regardless of whether it's TMS, TES, TIPS, TBDMS. Doesn't matter. Fluoride will take it off. So silicon is acid sensitive, but it's more fluoride sensitive. So this now gives us our pairs. I'm sorry, I'm just going to make the comment here because I did that for all of them. Acid sensitive and fluoride. Base plus hydrogen resistant. So the nice thing here is now we sort of have a matched pair of three different types of protecting groups. We've got acid sensitive ones, we have base sensitive ones, we have hydrogen sensitive ones. But that doesn't help us very much if we're trying to figure out how to selectively protect an alcohol. So let's say we have an alcohol or a sugar. Okay. So if we're thinking about that and what we've got going on here, this guy here is a primary alcohol. Everything else is secondary, so it's different. It's less sterically hindered. This is the second most reactive alcohol on the sugar, and that's because it is equatorial and it is adjacent to an axial alcohol, which is less sterically hindering on it than being adjacent to an equatorial substituent. Equatorial adjacent to axial. Then we've got number 3, which is equatorial adjacent to equatorial. And that leaves this guy's number 4, axial. Now, number 1 is actually quite a bit more reactive because it's less sterically hindered. 2, 3, and 4 are pretty freaking close together. Like, yes, if you control the temperature to a fraction of a degree Celsius, you'll be able to get like a 60-40 mix. That's not particularly useful. We need something better than that. And so what we want to do is we want to take advantage of the fact that these alcohols are next to each other and you can do different things with them. So we can selectively try and protect one over the other. So let's think about what happens if we take, just use an example we just saw. We take this guy and we treat it with TIPS, one equivalent of TIPS chloride. And some Benzyl in dichloromethane. So TIPS chloride is clearly bulky. It's got 3 freaking isopropyl groups on it. Good, I have more Pepsi. I'm snoozy. So we can take advantage of that because it's bulky, it needs space. The primary alcohol's got space because it's primary. So we can actually selectively, with one equivalent of this, put the TIPS on the primary. So bulky goes primary. And we can take advantage of that to make different types of protecting groups. Now, there's no benzyl equivalent because we actually start running into problems with this, but there is an acetate equivalent, which is the PIV group. That bond is stupid long. I'm going to shorten it up. There we go. So we have the PIV group. This is all this is a terbutyl ester. But if we call it a terbutyl ester, then everyone can understand what we're saying. So we say it's a pivyl oil group. The real reason is because pivolic acid was discovered before the relationship between that and the terbutyl group was known. So the name just is inherited from history before we knew about structure. But we have this thing. It's big and bulky. It's going to go on C6. TBS tips also go C6. So this is our first case here where we're seeing some selectivity, where we're seeing a way that we can selectively protect one alcohol in the presence of the other free alcohols. For all the ones we've seen so far, the benzyl protecting group, the acetates, most of the silicons, though we kind of are reintroducing two of them here, you don't really get any selectivity. You don't get preference for one or the other. With this thing, something we are. Okay, that's cool. Now, something else we can do with this. And that's that let's not treat these guys in isolation. So, oh, by the way, the pivotal oil, you deprotect the same way as an acetate. Which is convenient. So sodium methoxide, methanol, takes off the pivotal oil group. So let's say we have this guy here. If we treat this with it's basically a benzaldehyde equivalent. It's just set up to do this better than benzaldehyde does. It's the benzaldehyde dimethyl acetal, a little bit para-toluene sulfonic acid. If you don't know what that is, go look it up. And normally the solvent would be THF is a good one for this. And we do this at room temperature. And what we get out of that mixture I always draw this too close to the top of the page when I do this. Always, always, always. And it squishes up there, and then I get irritated. And then I surprise myself every time and forget about it. And do it again. I'm sure I'll do it again later this lecture. So what we end up getting is we end up protecting the C4, C6 alcohols, leaving the C3 and C2 free. So what's special about that? Well, what's special is that we're making a 6-membered ring. And we have one substituent on that terminal carbon, it's a phenyl group, and we can make the 6-membered ring such that that phenyl group is equatorial. That's very stable. And it's always equatorial. So how is this happening? Normally you can do this with quite a bit of heat as well. So it's happening because this is the most stable version of this guy. This is the thermodynamic product. So what can happen initially is this can react with any of the alcohols, but that's all going to be reversible. Everything is reversible. And once it makes the most stable conformation it can, that's where it locks in. So, excuse me, what we're doing here is we're taking the dimethyl acetal, and we have acid, and when in doubt, protonate something. Sorry, that's an H. Only one thing makes sense to protonate. Well, that's not going to stick around very long. Thank you very much. Kick you out. And now look what we've made. We've made this poor carbonyl, which has an extra carbon on it. Now, if that was just a hydrogen, that would be easier to remove, break the hydrogen-oxygen bond, neutral molecule, yay, everybody's happy. But no, we've got a carbon. So that's a really hot electrophile. So your sugar, which is wandering around minding its own business. Let's react the C6 first. It's most likely to react first because, again, it's the least hindered of all the alcohols. And so all else being equal, the least hindered is going to react first. Basic kinetics. We got something like this. Now, this can go back. There's nothing stopping it. The H is still here. The most likely thing to happen is for it to revert back, and it goes back and forwards endlessly, and that definitely happens. But we can get a proton transfer. And then if that happens, I'm just going to see if I can use the select function. Maybe if I use my cursor. No, I probably can't do it in... Yeah, I don't think I can do it when I'm in the middle of drawing. I can probably move things around when I'm not drawing a live presentation. Because what if we just protonate the other oxygen? Well, now it looks like suddenly the shoe is on the other foot, and the leaving group becomes that methanol. Okay, now we're back to the same problem again of having an alcohol or a carbonyl or an ether. Yes, it's an ether, it's a carbonyl, it's both, I guess, being positively charged. But we have an alcohol in close proximity, so let's just shut that closed. And that takes us up to the product after loss of the proton. And the big thing here is we make the six-membered ring. I already have it up there, but it's really important, so I'm going to write it again. And again, this comes down to the idea that we have a single substituent and we can put an equatorial. So just keep that in mind because, well, that's cool. I now have C2 and C3 open. But what if I don't want to do that? What if I want to do something else? Well, okay, I've learned my lesson. I'm drawing a little bit lower on the board this time. Take a very similar molecule. Benzaldehyde dimethyl or acetone dimethylacetal. Now, curiously, this one's going to mess with us a bit. I want to make sure I get this right. That's stupid. These are all stupid. That's good. So what we're actually going to walk away from here, this does work. It's not as good as I'd like it to be. Is we protect, notice I've drawn galactose. We protect the 3 and 4 positions. Now why is that? Well, suddenly 5-membered rings do better with pseudoaxial substituents. So if we have 2 methyl groups on that carbon, one of them is going to have to sit axial if this made a 6-membered ring, which would be bad. But if it makes a 5-membered ring, there's a way for it to sit pseudoaxial, and they're both kind of out of the way. So the 5 is actually more stable for these dimethyl acetals than the 6. So in the benzylidene, it was because there was one substituent. There was a hydrogen and a phenyl group, and a big phenyl group could sit equatorial. Whereas with this one, you'd have one of those axial if you went to a 6-membered ring. So it chooses instead to go to the 5-membered ring. So in this case, what we end up getting is we end up protecting carbons 3 and 4. And why do we get that? Because they are cis diol. Are more easy to protect. I guess more easy is easier. As a ring than a trans diol. So one axial, one equatorial, this will always win. So the mechanism is identical to what we just saw with benzylidene, dimethoxybenzylidene acetal. It's the same kind of idea. I'm not going to draw the same mechanism again. It's absolutely the same. It's just, it can make that everything's in equilibrium. It falls to the thermodynamic sink, and that is the cis here. The final one we could really tackle this with is, let's say we had a glucose like this. Work with lactose too. We use a slightly different reagent. And this gives us a kinetic product. And that's because we're really shutting down one of the equilibria. We're reducing the amount of methanol present, because we're not going to get 2 equivalents of methanol every time. We're only going to get 1. And that's going to really, really change the dynamics of how these things work. So we're going to have basically a kinetic process here. So this works by attacking like that. No surprise. Oh, look, it's this hyperactive electrophile. Sure, chemists are not creative. You see the same freaking patterns over and over again. So we have the same carbonyl ether thingy that we've been dealing with over the last 20 minutes or so. And of course, what reacts first? The least hindered site. So the C6 reacts first. I'm going to just draw a line through this so we'll kind of talk about something different. That's going to give us I'm just going to draw on this side because it makes more sense. This guy. So although these acetals like making 5-membered rings if they are in equilibrium. This is not really in equilibrium the same way. This is completely one way, because you don't have that other methanol that can come in and take care of this. So we're then going to kick that out. This, of course, is in equilibrium. And we have basically the same thing we saw with the benzylidine. And so that's going to ring close onto that. Something weird happened there. And we get a 5-membered ring or a 6-membered ring, and we still have these two OHs. And we know this likes making 5-membered rings, so this repeats. And we protect 2 and 3 also as the acetal. So we have options here. Like if we really watch the number of conditions, we could just protect 6 and 4 if we just watch the number of equivalents. But you know what? Why not use a benzylidine for that? It's more accurate. But we can protect both. Or we can use this top set of conditions and we can protect just 3 and 4. If this was glucose, we would get basically a 50-50 mix of 3 and 4 and 2 and 3. But it's not glucose, it's galactose. I just picked that for a reason. I think we'll do an example with glucose in class on Tuesday. But this gives us quite a lot of opportunities here. Because now let's say we did this top one here. I could protect C6, which would leave me C2 free. Or I could protect C6, then protect C2, then deprotect C6, which would leave me C6 free. So I have ways to modify this and play with this to get these different ones free. Okay. Now, how do we deprotect these? Well, the most interesting one, I think, is the benzylidine that we started with. So the numbers I'm going to use are for glucose. It works equally well for basically any of the sugars. It doesn't matter. Let's say we had this. Then we protected those OHs by taking, I don't know, why not, TES and Benzyl. And so we put TES on those two. Now, that benzylidine up there, oh, I didn't talk about how to deprotect benzyl groups, did I? I just skipped over that. I'll have to go back to that. That benzylidine up there, we can take it off completely by treating that with hydrogen and palladium. This is also how you take off any benzylidine. Or benzyl group, sorry. This is called a benzylidine. That's great. We've deprotected C4 and C6. We had C2 and C3 protected because we were able to put the TES groups on there when C4 and C6 were protected. So we've managed to kind of free that up. And now I could access a deprotected C4 by protecting C6 with something, because I can take advantage of the fact that C6 is primary and C4 isn't. So I have a good way to get to C4. But, you know, somebody else thought, I think what I can do is maybe I can selectively break this bond or selectively break that bond. And if I can do that, then I don't need to play this game putting another protection group on there. I can just selectively open one or the other and end up with a benzyl group. Now to do that, what I need to do is I need to reduce that carbon-oxygen bond. And so it's unsurprising that you use reducing agents. If you use H plus in the presence of sodium cyanoborohydride, you haven't seen sodium cyanoborohydride in a while. It's a very, very gentle reducing agent. It's kind of like sodium borohydride on soporifics. It doesn't reduce much of anything. It's really good for reducing imines. But it will reduce benzylidines. And so what ends up happening is that you protonate the C because it's small and it's a tiny little nucleophile, and this is a secondary alcohol, and secondary alcohols are slightly more electron rich than primary alcohols because of donation of the carbon-carbon bonds. You get selective protonation of that. So we follow that through. What's going to happen? Well, we're going to protonate that. No. I really don't want to redraw it, but I really should. And I'm just going to change my arrow so it's going straight down. And the H plus for this is generally a little bit of HCl. So I'm just going to actually sketch an HCl. Not a lot. Kind of small amount, like 1 equivalent, 2 equivalents. You don't need a lot. But now, of course, when you have the borohydride coming in, that's looking for where to deliver the hydrogen. And so it's going to deliver this hydrogen to that carbon. This oxygen's already chelated to a hydrogen, so it's a good leaving group. And so that's what we see as we break that bond. And what does that leave us with? Well, there's a phenyl, there's a hydrogen, there's an oxygen of sugar, and of course all this is a benzyl group. So what we managed to do is we managed to cleave that bond so that the benzyl group falls onto C6, and we leave C4 as a free OH. Now, we also have conditions where we can invert that. So as I said, the whole idea here was the H plus was a nice small proton. That oxygen is more electron rich, but it's also more hindered than the C6. So if we can invert that, if we can find a way to put something big in there, a big acid isn't going to be able to interact with that C4. It's going to want to interact with C6. And that's exactly what happens. So if we take a big acid, so small acid, you don't get much smaller than H plus. Now if we take a big acid, you know what? I'm going to start a new page. What if we use a big acid? So you're thinking, okay, H plus is acid. You can't make H plus bigger or smaller, and that's absolutely true. But H plus isn't the only type of acid. We can use a different type of Lewis acid. That's what we're going to do. Forgive me. The other thing I do besides writing them up at the top is I write them too close to the edge, and I write into that. This is when I hate sugars because there's so much left to write that really doesn't matter at all. I'm actually just going to draw like that so we don't have to draw the rest of the sugar. So if we treat this with something huge, boron, dibutyl, butyls are big, and we have a triflate on here. Triflates are really good leaving groups. So a way to think about this is almost a B plus triflate minus. Like that boron triflate bond almost doesn't exist already. So we already kind of have a B plus here. That's good. We want B plus. And then we toss in, you know, it works with sodium cyanoborohydride. You know what? I'll leave in sodium cyanoborohydride. It's not actually the best reagent for this, but there's no reason for us to make life more difficult by introducing different reducing agents. Let's stick with that. So now if we're looking at this guy, that's huge. And so now we've got this huge boron, these big wavy butyls. And by butyl, I mean propyl, apparently. Well, if I'm sodium cyanoborohydride, I know who I'm kicking off now. I'm kicking off that C6 alcohol instead of the C4. Because now I've got a big bulky group. It's gone to the place it can go because it's more accessible. And so the delivery of the hydride is going to break that guy, which will give me after workup and cleavage of the boron, C6 free. So this is cool. So depending on which Lewis acid I use, or acid I use, I can get either C6 or C4 free with the benzylidine. With the acetonides, we don't have that kind of selectivity. You put the acetonide on, you take the acetonide off. How you take acetonides off? Well, let's just show an example with both of them. So let's say we made this. We treat that with water and some acid. And we are going to cleave off both of them in an exact inverse mechanism of how we put them on. It's almost arrow by arrow. You just go backwards. And what drives this time is we have lots of water. Last time we had lots of starting material. We were drowning in the thing that wanted to make acetals. Now we are drowning in the thing that wants to make alcohols. So we've talked about acetonides. We've talked about benzylidines. We've talked about sialoprotection groups. We've talked about esters. The last ones I want to talk about, I think I actually want to go through in class because they're a little bit more detailed, and that's a boronic acid, boronic ester, and tin esters. And so we can get some more selectivity there as well. And so I think I want to cover those two in class. Those are the distanines and the boronics. And then we'll talk about the different types of, well, you know what, I can talk about the different types of benzyl esters, right? Benzyl ethers right now. So again, I breezed over this. But if we have all these benzyls, we put them on using sodium hydride and DMF. We can take them off using hydrogen gas and palladium. There are lots of other ways too, but that, you know, on paper, you don't need lots of ways. You need one. If you want to give me another one that works, go nuts. But what if I want some selectivity here? And so we have two different subtypes of benzyl groups because the problem is, you know, this is a little harsh depending what else you have. If you have any double bonds in there, you're in trouble. So we like having specialty benzyl ethers, and I want to make sure I find the right page for that. Good. So the two that we're going to talk about are the paramethoxy and the paranitro. And we're kind of making use of the fact that we can take care of aromatic chemistry this way. So let's say we had made this. Let's not worry so much about how we would have made that right now. You've actually seen enough ways to make this if you put the pieces together. And again, I'm going to puzzle through some of those. So we can make this from the alcohol. And the benzyl chloride of the paramethoxy benzyl alcohol. So those are the reagents. This looks neater on my chem draw. Okay, so we can make this. Now if I want to take this off, which this wouldn't make a lot of sense, I put it on, take it off in an immediate step, that's absolutely insane, is I would use DDQ and water. And what is DDQ? Well, DDQ is a weird quinone. Dicyano-dichloroquinone. So what is going on here? Well, we're going to move some electrons around. So what we're going to do is we're going to transfer an electron from DDQ to the sugar. So what does that look like? I am going to draw down here. single electron transfer into the arrow ring of this system. So we suddenly put an electron into a SOMO, like a singly occupied molecular orbital, and DDQ has gone positive. And this system has gone negative. So we have I'm going to represent it like this for now. That is obviously not a stable thing. It's got a negative charge, it's got a radical. That's not going to last. I'm actually just going to move those around. Sorry, no, I got that. See, this is why I'm recording. I'm probably going to have to go delete that. We're going to do the other way around. I'm going to transfer an electron from this methoxy. I thought that was weird. To DDQ. I'm going to end up erasing this part of the lecture so I don't look like such a fucking idiot. And I always get this wrong. I always get this wrong. And then I have to invert myself. And you think I'd probably double check this. I go, no, I'm going to get it right this time. I know I'm going to get it right this time. And I don't. Because that would be a miracle. And we can't have that happening. So we get a system that looks like this. This is obviously not very stable. You got an oxygen missing an electron, and we have something happening to the DDQ where it's negatively charged and it's got a radical and we broke a bond. Now, you can start seeing what's probably going to be happening next, because look at that. I like where this is going. Why? Because I'm starting to look like quinones are an abomination because they aren't aromatic and they really should be. You want them to be aromatic. You're just like, come on, just make some double bonds, but they can't make double bonds. But of course, DDQ can accept that electron really well because you have all the resonance. I'll leave this as an exercise out into the cyano groups and all the inductive withdrawing of the chlorines. Now, if you have DDQ with 4 cyano groups on it, you're thinking, well, shit, chlorines are inductive. They're not amazing. I'd really like to have 4 cyanides. It would accept electrons amazing. Oh, yeah, it accepts electrons amazing. That doesn't exist as a quinone. It, like, in a shot, it goes to benzene when you look at it. So it's not a useful reagent. It's too reactive. DDQ is this careful balance between being a good electron acceptor to do this kind of chemistry, but not being too good an electron acceptor that does this kind of chemistry before you want to do this kind of chemistry. And it's that balance that's really, really important. Whereas it's really, really important that we have this system here because we can stabilize these kinds of molecules. So what we can think of here and happening here is that, I want to make sure I do this right. We can move the electrons over like this. So let's do that and flip the page. And so we're going to keep track of what's going on with DDQ and what's going on with this other molecule. So our DDQ again at this stage, O minus radical here, thing here, lots of chlorines, some cyanides. It's awesome. And then on the other molecule here, we've got something that looks like that. Well, we can resolve part of this issue. Again, pause for effect. I gotta lose that fucking proton. I won't lose it as a hydride. Oh, I always was wrong. You know what? I'm just gonna do it instead of worrying about trying to figure out. I think that's wrong in there. So what we can do here is we can lose the radical. So we're going to grab this proton from here. That's going to kick onto here. And that's going to give us so now we have a neutral species. We got a radical, we got a negative charge. And we've got the DDQ sitting over here, which now just has a radical. And it's neutral. So we know what we want to do. If we follow this math over, we want DDQ to aromatize because we want aromatics. And that's neutral. And this guy is now also neutral and it's got an extra electron. But if we donate this electron over to DDQ, again, we've already donated one electron. Now we're donating a second electron. What we end up with is oh, look, we're out of radical chemistry, so we can all breathe a sigh of relief. Negatively charged over there. And on this guy over here, we've got a negative charge next to a positive charge. Of course, that's not, we're going to let that stand. We're going to make a double bond. So now we have that. Not particularly stable. So let's draw a resonance structure of that. much better. Except now, oh look, we have a problem because we have our oxygen making two double bonds like that. But that's what we were just dealing with all those acetals. Put page. You know what? I'm not going to edit out that stumbling around. I think it's really humanizing when you see your professor completely fucking lost when he's trying to figure out what the hell some moron has written in a book. I'm going to leave it in there. Mostly because I'm just too lazy to edit anything out, because that actually takes time and effort. I am going to cut this talk, though, into a couple different ones. Later, I'll just make sure it's up today. That's the important thing. So, H2 plus, we swap a proton around. And it's unsurprising, then what we do is we release our alcohol. And we generate the aldehyde of that paramethoxy group. So overall, what happened here was we took ROH, RO, treated that with DDQ and water, and we got ROH, where R is the restless sugar, plus this aldehyde, plus we took DDQ and we aromatized it from this unnatural hydroquinone to a diphenol. Mechanistically, bit of a pain in the ass to draw it. Chemically, really straightforward. Like this is easy. And DDQ doesn't touch any of the other protected groups we've seen. So you can have anything else on there. DDQ is completely selective. So you get DDQ interacting with only this protecting group. Now, the match to that is to use the nitrobenzyl. Now, I don't want to use that. That's light sensitive. So, yeah, I think what we're going to do is mostly talk about the how you can do this photochemically for these guys. And you know what? I'm going to leave it off. We're not going to talk about nitrophenol. Oh, screen sharing is paused. Resume share. I'm going to leave it there. I'm tired. That's an hour and 20 minutes. That covers. We're not going to need the nitrobenzyl anyways. So we covered the acetate. We covered the acetate is base sensitive. You use nucleophilic, you take it off. Benzyl, you know what? This is worth writing. Summary. Because there's a lot of information here. Acetate. Base sensitive. Benzyl. H2 sensitive. silyl, H plus sensitive, /F minus sensitive. So you have to be a little bit careful because some of the conditions we have for glycosylation, we're using F minus, those are not suitable for use with the silyl protecting group. We had the acetonides, protect two at once. Like 5-membered rings. Like cystiols. Then we had the benzylidines. Protect two at once. Like 6-membered rings. You don't really get 5 no matter what you do. You can't really make it go 5. It doesn't. I can probably count on my one hand the number of times I've seen benzylidines using to protect a 5-membered ring, like anything that's not a C6 oxygen. So they really are selective for C6, C4. Almost exclusively. I'm going to say almost because I am sure there are exceptions. But almost means exclusively. Then we talked briefly about the para-OMe benzyl. Well, we didn't talk briefly. We spent a lot of time with me stumbling around with that. Uses DDQ, completely selective. Deprotection. You can also deprotect it using H2 and palladium. That works just fine. So this gives us actually enough different ones to be able to selectively sort of protect whatever we want, open up whatever alcohol we want. And next class on Tuesday, we are going to go through and we're going to see different examples and how we can actually put these into use to get specific alcohols free from different kind of starting positions. So I'm going to leave it there.